Problems 4.2, 4.6, and 4.17 will be covered in this video. Problem 4.2 says there is a charged particle, 1/2 coulomb, moving with a velocity of 10 meters per second in a magnetic field of 10 Webers per meter squared. So here's the drawing. We have our charged particle moving with a velocity v and the magnetic field b. And velocity and field are vectors, so the angle between those is theta. Now the magnitude of the force is given by Q times V times B times sine of theta. Therefore, the maximum force that we're going to be able to get is QVB, which is 0.5 times 10 times 10, and the units work out to where that is in newtons, so 50 newtons is the maximum force. Now, if sine of theta is 0, that's the zero force case, and that occurs whenever V is parallel to B. On the next problem, we are asked to find an expression for the sensitivity of this circuit with respect to the resistance. So here's the equation for the sensitivity of the current with respect to resistance. And current is shown here, so I. Here is the expression for current, and we just want to find the sensitivity is the derivative of current with respect to resistance, so how quickly the current changes as resistance changes. So we just take the derivative of this function with respect to r, and we end up with negative e over the sum r plus ri squared. And we're also asked to find the condition for the highest sensitivity. Well, in this case, we're talking about configuring ri to get the highest sensitivity. So R varies, that's what we're measuring. So we want to say, what's the Ri that'll give us the highest sensitivity? If we look at this expression, the biggest value that we can have if Ri is a variable would be, for sensitivity, would be if Ri is 0. That would just be E over R squared. So the highest sensitivity possible is when Ri is equal to 0. The last problem has to do with a voltage divider circuit. So that's shown here. We're measuring this voltage E, and our voltmeter has some finite resistance Ri. If we just had an open circuit here that we were measuring E across, in other words, Ri was infinite, then the relationship between E over E0 to R over Rm would just be linear. So ideally, E over E0 would equal R over Rm. That's for the case where Ri is infinite. But what actually happens is we get this curve. So that's a nonlinear relationship. Let me draw that in a little darker. And this is the actual ratio of the voltages, E over E0, that we get when we have some finite resistance input impedance in our voltmeter. Now, the problem in the book, 417, says what happens if we put an end resistor here. And first of all, it asks you to find an expression for the output voltage. So here is the expression for this case, output voltage, R over Rm and Ri. And if we wanted to find a similar expression for this circuit, then we would just be replacing R in the original circuit with R plus R1, and Rm in the original circuit with Rm plus R1. So we're concerned with the ratio here. This resistance as a function, as relative to the total resistance. So we want R plus R1 relative to Rm plus R1. So to find the expression, we simply substitute. So we replace R with R plus R1, and we replace Rm with Rm plus R1 in this equation. And that will give us the ratio of the voltage measured to the input voltage. And the question also asks, so what's an advantage of this? Let's see if I can sort of illustrate the advantage. The loading error is the difference between the behavior we would expect or want to see and what we actually get due to our finite input impedance in our voltmeter. And the error is the difference between the two. The error is 0 at the ends when R is equal to, in this case, 0 or Rm. So here there's no loading error, and the biggest loading error is in the middle. I tried to show that with this drawing. Now, if we have, so as R varies from 0 up to RM, we go all through this range of loading error. So we have small loading error, big loading error, and little loading error. And it would be nice if we could change this value. R would go from 0 to RM, but we could stay over here where we have just a small loading error. So again, this ratio here from 0 to 1 is the ratio of the measurement here to the total measurement. And if we were to add a big resistor here, then as R changes, the ratio is just going to change. Say R is 7 times bigger than RM, then, I'm sorry, R1 is 7 times bigger than RM, then this ratio here is going to be 7/8 at minimum to 1. It'll vary from 7/8 all the way up to 1. And so that would mean that we'd be operating in this range here where we have smaller loading error.